everyone, and thank you for standing by. All participants have been placed on a listen-only mode until the question-and-answer session. To ask a question, you may press star 1 on your touch-tone phone. Today's conference is being recorded. If you have any objections, please disconnect at this time. I would now like to turn the conference over to Dwayne Brown. You may begin.
Well, thank you, operator, and good afternoon, everyone, and thanks for joining us. Again, my name is Dwayne Brown with NASA's Office of Communications. Today, you will hear about the initial science observations of Comet Siding Spring's close flyby of Mars that occurred on October 19th. We'll have presentations from our speakers and then open it up for questions. And the speakers will be using graphics for today. To access the visuals, go to www.nasa.gov/Mars/telecon. Again, to access the visuals the presenters will be using today, www.nasa.gov/Mars/telecon. In addition to our primary speakers, there are scientists involved in the mission that are on this call, and perhaps during the question and answer period, they will provide additional details about the findings and what those findings may mean. They will identify themselves before providing additional information and details. And again, this is truly a team effort, so you will probably be hearing other scientists during the Q&A. We have a lot to cover, so let me introduce you to the key speakers for today. First up, Jim Green, Director, Planetary Science Division, NASA Headquarters, Washington. Nick Schneider, Instrument Lead for MAVEN's Imaging Ultraviolet Spectrograph, University of Colorado in Boulder. Mehdi Benna, Instrument Scientist for MAVEN's Neutral Gas and Ion Mass Spectrometer at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Don Gurnett, Lead Investigator for the European Space Agency's Mars Express Ionospheric Radar. And Don is located at the University of Iowa in Iowa City. And Alan Delamere, Co-Investigator for Mars Reconnaissance Orbiter's High-Rise Instrument, Delamere Support Services in Boulder, Colorado. And to kick us off, I'll toss it to Jim Green.
Thank you very much, Dwayne. Well, on October 19th of this year, the comet Siding Spring passed by Mars at an incredibly close distance of 87,000 miles and at an incredible speed of 35 miles per second. Siding Spring is an Oort cloud comet, and it came from the furthest reaches of the sun's gravity, which is at about 50,000 astronomical units away, or 1 light year, it turns out. We believe this type of event occurs once every 8 million years or so, so it is indeed a rare opportunity for us to observe this. Now, Robert McNaught discovered the comet on January 3rd, 2013, at the Siding Spring Observatory in Australia, and therefore it is named Comet Siding Spring. Ever since its discovery, NASA's been getting ready for this big event. We have never before had the opportunity to observe an Oort cloud comet up close. You know, we get 4 or 5 Oort cloud comets coming into the inner solar system every year, and they just move too fast to catch up to. Instead of going to the comet, it came to us by flying by Mars. We are so lucky to have NASA's MAVEN mission arrive just in time to observe this once-in-a-lifetime event. Today, we are announcing a number of fantastic discoveries of both the comet and its interaction with the ionosphere and atmosphere of Mars. For the comet, we observed for the first time a number of important characteristics, such as its spin period, and we've bracketed its size. For Mars, the comet's dust slammed into the upper atmosphere, creating a massive and dense ionospheric layer, and literally changed the chemistry of the upper atmosphere. So now I'd like to turn it over to MAVEN scientist Nick Schneider to start us off on what we have discovered. Nick?
Good afternoon, everybody. Good morning. I'm Nick Schneider from the University of Colorado, and I'm excited to be here to talk about our discoveries at Mars. The fleet of spacecraft orbiting the planet has witnessed the aftermath of an intense meteor shower caused by Comet Siding Spring. And the evidence from MAVEN is vaporized metals deposited high in the atmosphere seen by 2 of our instruments. And these metals must have been placed in the atmosphere from cometary dust entering the atmosphere at 56 kilometers per second and burning up as shooting stars. We want to describe the observations because the data themselves are very compelling. And if you can all turn to the first graphic, Schneider 1, I represent the imaging ultraviolet spectrograph on MAVEN. This is a remote sensing instrument that studies the atmosphere by looking at the ultraviolet light which is emitted by the atmosphere. It allows us to figure out what kind of gases are present and how much. The observations I'll describe today were taken in the part of the orbit closest to the planet, shown here in red, where we actually dip into the upper layers of the atmosphere. The second graphic will show how it is we make these observations. As the spacecraft flies past the planet into the screen, our instrument looks off to the side and looks up and down within the atmosphere to, again, measure the composition and structure of the atmosphere, what gases are present and what amounts as we look up and down. And as the spacecraft moves along its orbit, we can actually construct a rough image from the combination of looking up and down and flying forwards through the atmosphere. So the third graphic shows the spectrum of Mars on a normal day. And in fact, every feature here has been well studied by previous missions. They all come from the emissions from carbon dioxide, the most common gas in the Mars atmosphere, and its breakdown products, for example, carbon monoxide and oxygen. All these features are very common in the Mars atmosphere, very steady, very well studied. And this is what we saw just before the spacecraft went into its protective mode behind the planet to protect itself from the dust from Comet sighting spring. And as soon as we could confirm the health and safety of the spacecraft and the instruments, we turned back on and started our observations again. We didn't get these observations on the ground for several days, and we were all wondering what we would see, realizing that the comet had faded in intensity, wondering if we would see anything at all as a result. We're all leaning into our screens, wondering what difference we might see, and if you go to the fourth graphic, you'll see what we did see. And in fact, we all were sort of pressed back in our chairs, seeing this booming signal that you see on the right-hand side, 280 nanometers. This is the unmistakable signature of ionized magnesium in the atmosphere of Mars. You can see here it was the brightest feature in the spectrum for a matter of hours, and it was completely absent, as you can see from the blue line, the previous spectrum that I showed you in the previous graphic. Now, there are a number of other differences. Just about every difference you see here is real. Some of the brighter ones are indicated by arrows. It's ionized magnesium, the brightest feature. The one to the right is neutral magnesium, and the ones off to the left are from iron in ionized and neutral form. These are not what you expect for atmospheric ingredients, but they are, in fact, what you expect from comet dust. You can imagine that iron and magnesium are very common, and in fact, in solid material, and in fact, Earth has iron as the number 1 ingredient and magnesium as the number 4. So these are not surprising ingredients to be present in cometary dust. And in fact, this kind of emission in the upper atmosphere has seen at Earth. There's magnesium, sodium, iron, other ingredients in Earth's upper atmosphere, but they're not associated with meteor showers. They're only found in sort of an everyday level from the meteors that arrive continuously. So what I'd like to do next is to show you that what you might have seen with ultraviolet eyes if you'd been near Mars on this day right after the comet closest approach. And if you go to the fifth graphic, you'll see this image that we've constructed as the spacecraft has flown along. Now, the orange here shows the emission from ionized magnesium, and you can see it stretches over a wide extent on the planet, limited by our observations. We actually expect it covered at least a hemisphere of the planet, and so it was not an isolated impact. We can use the brightness and the extent of the emission to figure out how much comet dust must have been deposited, and the answer we're coming up with is a few tons. It's very approximate with this preliminary analysis. Now, based on this mass, we can make a rough estimate of what the meteor shower must have been like. And it's looking like that meteor shower must have had thousands of shooting stars per hour, possibly what's called a meteor storm, although we're still working on the numbers. But numbers aside, it must have been a spectacular meteor shower on Mars that night. So apart from the show, the other significant effects are that it made a new layer in the ionosphere. These ionized magnesium atoms that we found there created an additional layer of the ionosphere. You'll hear more about that later. So the emissions that we saw endured for a few hours but faded over the days after the closest approach, probably due to chemical reactions, which we're still investigating. And in fact, it's a little surprising how quickly some of these materials are disappearing. We think the chemistry at Mars might be a little different than they are at Earth. Ultimately, we think that chemical reactions are going to turn these metals back into dust in the Mars atmosphere. It's called meteoric smoke. It's a phenomenon seen at Earth, and it could affect Mars' interaction with sunlight ongoing in the atmosphere. It could cause the creation of high-altitude clouds, and it's possible that it could change the chemistry of the atmosphere just from the addition of these new ingredients. So to summarize, we saw intense emissions from magnesium and iron in the Mars upper atmosphere. These must have come from the vaporizing dust entering the Mars atmosphere. And the differences between the behavior at Mars and the behavior at Earth are a sure sign that we're going to learn something interesting about the chemistry of meteor showers. The debris created a new temporary ionospheric layer in the Mars atmosphere, may have long-lasting effects, and we'll be studying all of these over the coming year and keeping an eye out for more meteor showers. Now I'd like to turn the presentation over to Mehdi Benna.
Thank you, Nick. I am Mehdi Benna, the instrument scientist of the Neutral Gas and Ion Mass Spectrometer, and I will be talking to you about the many metal ions that Engham's instrument has detected following the passage of Comet Siding Spring. So my first graphic, Benna 1, is just a reminder of the context of these Engham's observations during Siding Spring. And like Nick told you, what's exciting about the detection of metal ions is the fact that this is the first time we can link these detections to the recent passage of a specific comet, and more importantly in our case, an Oort cloud comet. And also the fact that this is the first time we make such detections in the Martian atmosphere. In my second graphic, you can see a picture of the neutral gas and ion mass spectrometer that carried out these measurements. Engham's was built in the Planetary Environment Laboratory of the NASA Goddard Space Flight Center, and it's used by the MAVEN mission to characterize the composition of the upper atmosphere and the ionosphere of Mars from an altitude of about 500 kilometers down to about 120 kilometers. The instrument is mounted on the Spacecraft articulated payload platform, and it's regularly pointed toward the spacecraft direction of motion to allow it to properly carry out its measurements. In my third graphic, Benna 3, you can see in the top plot an example of the ion detections that Engham's made. I'm showing here as an example the measurements made of iron in its ion form. The observation campaign started a day prior and lasted for 3 days after the passage of Siding Spring, which is here is indicated by the vertical line. And the missing data points around the time of the comet's closest approach, it's due to the fact that the instrument was turned off temporarily during the peak of the dust flux to minimize risk on the hardware. So as you can see, the ions of iron were not found prior to the arrival of the comet. They peaked significantly a few hours after its passage, and then they were all gone within a day after the comet flew by Mars. So the sudden appearance and the temporary nature of this profile points directly to the cometary origin of these ions as being the result of ablation of cometary dust particles as they streamed through the atmosphere of Mars. Also, we were able to further confirm that we are dealing with iron and not some mass interference from another species by looking at the isotopes. As you know, most species have multiple type of atoms with different nuclear masses that we call isotopes. And for a given element, the ratio of the minor to the major isotopes can be used as a fingerprint that enables its unequivocal identification. So, for example, here, iron has 4 stable isotopes, and we were able to detect the 3 most abundant ones during the sighting spring passage. These are iron 56, 54, and 57. And by comparing the ratio of iron 54 to iron 56 and iron 57 to iron 56, which you can see here as a red dot with the arrow bar in the bottom plot, so by comparing these ratios with the ones that occur in nature, which are shown here by the blue dots, we were able to unambiguously identify the species as being iron. And so this exercise was done for 4 other metals out of the total 8 elements identified by Engels. In my 4th and last graphic, I put in a time series similar to the one I just showed you for iron, but now for the 8 metal ions that were detected by Engels. These metals are sodium, magnesium, potassium, chromium, manganese, iron, nickel, and zinc. And as you can see, all these species peak in a similar fashion following the passage of sighting spring. So what's really exciting here is that using these measurements, we can ultimately characterize the elemental and isotopic composition of this cometary material. They came to MAVEN as a free sample from no less than an Oort cloud comet. So with that, I will turn over the discussion to Don.
Good morning. I'm Don Gurnett, lead investigator for the Mars Express ionospheric radar. I'm going to talk to you today about some very spectacular results, namely the detection via radar sounding of a very dense layer of ionization in the upper atmosphere of Mars. This layer is caused by high-velocity impacts of small dust particles from sighting spring, i.e. meteors. These observations were made not only by the Mars Express radar, which I am involved, but also by a somewhat similar subsurface sounding radar on the Mars Reconnaissance Orbiter, which I shall also briefly discuss. Now, let's take a look at slide 1, which shows the Mars Express radar. It's a very special radar. It operates at very low frequencies, namely 0.1 megahertz to 5.6 megahertz. And at such low frequency, we have to use a very long antenna, and you can see that antenna there. It's 130 feet tip to tip. Now, this frequency range is ideal for ionospheric sounding. It's in the range of the characteristic frequencies in the Martian ionosphere, a frequency we talk about in plasma physics class called the plasma frequency. The radar is also used on the night side of Mars for probing the subsurface of Mars. Those measurements are limited to the night side where normally no ionosphere exists. In other words, the ionosphere does not get in the way of the subsurface sounding signals. The spacecraft has an orbit of 7 hours, and it's somewhat elliptical orbit, and we take data mainly at the low altitudes below about 1,200 kilometers. Now, if you go to slide 2, let me tell you how the ionospheric radar works. We depict on this slide the Mars ionosphere. That's essentially a plot of density as a function of altitude. And the radar has a special feature, which it sends out a pulse at some frequency, let's say 100 kilohertz. Then it moves to the next higher frequency, sends out another pulse, which reflects off the ionosphere. And finally, as you move up in frequency, you get to a point where the radar signal penetrates through the ionosphere and reflects off the ground. That allows us to measure the maximum density in the ionosphere. That's the basic principle by which it works. There's a direct correlation between frequency and density. Now let me move to slide 3, and I'll show you the spectacular effect that we saw almost as soon as we looked at the data, which was just a couple days after the closest approach. Now this slide shows 3 what we call ionograms. They show altitude, where the reflection occurs, and the color indicates the intensity of the reflected signal. The dark blue is essentially essentially the noise level of the receiver. So, in the top panel, for example, we essentially see no signal at all. The horizontal axis there is the frequency that we're transmitting. Now, the top panel is from the orbit when sighting spring was the closest to Mars. And it was predicted that any dust from sighting spring would probably take about 100 minutes or so to finally reach Mars, and as you can see, we see nothing there. Then 7 hours later, we go through the same region, which is on the night side of Mars at a high latitude over the polar. All 3 of these are at that high latitude in the night side. And we see a great effect, which can be seen in the green kind of horizontal line that goes all the way up to 4.6 megahertz. That corresponds to a density of about 2.6 times 10 to the 5th electrons per cubic centimeter. And you can read off from the altitude that the altitude of this layer is about 80 kilometers. It's a little fuzzy just what the altitude is. We are quoting about 80 to 100 kilometers. That's well below the the peak in the ionosphere that we normally see on the day side. Of course, this is the night side, so we don't expect to even see the ionosphere. So this is extremely unusual. And then 7 hours later, the effect is gone. So let me show you a different latitude on the next slide, slide 4. This is now closer to the equator, latitude about 45 degrees. And in the upper panel, you can see the normal ionospheric trace. We're on the day side of Mars now, and it goes up to about 3 megahertz. That's on the top slide. The middle slide, just like over the polar cap, we see not only the ionosphere on the day side going up to about 2.7 megahertz or so, but we see the same dense ionized layer, not to quite as high a density. In this case, is about 2 times 10 to the 5th electrons per cubic centimeter. You can also see the reflection from the ground there, and by comparing those two, you can again show that it's at an altitude of about 80, perhaps up as high as 100 kilometers. And then 7 hours later, the effect is completely gone. So the result of this radar sounding is summarized in slide 5, which shows the normal ionosphere as you'd see it on the day side of Mars in red, and then the dense enhanced ionized layer at about 80 to 100 kilometers created by dust impacts. By the way, we concluded it was dust impacts just a few days after we got the data, because that's the altitude that we know that dust from other much weaker meteor showers that have been seen before, they're at about that altitude. Now, let me on the last slide, slide 6, comment about the Mars Reconnaissance Orbiter result. They have a somewhat different radar that's designed, it's at a higher frequency, and it is not designed directly for detecting the ionosphere. What it's intended for is sounding the subsurface of Mars to search for water and ice. Now, this radar uses a type of signal that's caused a chirp, and during the radar pulse, the frequency is rapidly swept. And then that signal goes down, reflects off the surface of Mars. Then it's reconstructed in a way that gives you a much better accuracy in terms of range than we have with the ionospheric radar. And the top panel shows the reflection off of the surface, and it's very sharp, as you can see. Now, during a pass, it was about 2.5 hours after the closest approach of sighting spring. A radar pass was from Mars Reconnaissance Orbiter, passed over the night side where there should be no ionospheric effect at all. And you can see the trace from the ground is now significantly blurred. That's the bottom panel. And this blurring is caused by ionization between the spacecraft and the ground that sort of messes up the chirp signal. It delays it just a little bit so it doesn't appear sharp. And one can then, by adjusting the deconvolution of the chirp, you can determine you can actually estimate the total ionospheric content. You can't directly sound off the ionosphere, but you can get a total idea of the total number of electrons in a vertical column, and that is quite consistent with the numbers that we've come up with the Mars Express ionospheric radar. So to summarize, we've detected a very dense layer of ionization in the upper atmosphere of Mars over an extended region for about 7 hours after the closest approach of the comet, and is just virtually certain this is produced by high-velocity impacts of small dust particles that came from sighting spring. So let me turn it over to the next speaker, Alan.
I'm Alan Delamere, a HiRISE co-investigator, and I'm going to address the problem of tracking the comet, give you some information on the initial rotation results, and the search for the nucleus. I started looking at comet nuclei with Comet Halley, and I'll get back to Halley a little later in the presentation. The HiRISE camera, as most of you know, is a very high-resolution camera looking at the surface of Mars, and we have successfully used it to look at Earth, Moon, Jupiter, and stars, and of course now we looked at ISON and now Siding Springs. So our first task was to confirm the trajectory of the comet past Mars. And this is a critical feature because we only have a small field of view with HiRISE, and therefore it was important that the spacecraft was looking in exactly the right direction. So that high speed, 56 kilometers per second, and the rapid transition that takes place because it's very close to Mars means the spacecraft has got to really follow that very precisely. A team of observers and navigation specialists worked on this for about a year, and the final adjustment was made by the HiRISE camera 12 days before closest approach. So if you turn to the next slide, Delamere 1, you'll see one of the pictures that we took at minus 12 days. Now, if the red square wasn't there, you'd say that we're just looking at noise. But fortunately, we took 3 images, and lo and behold, that noise blip was in the same place for each one. We then measured its position with respect to the stars and came up with an ugly surprise. The comet wasn't in the right place. And the reason is that we were looking at it from a different viewpoint compared with most of the observations were done from Earth from a different viewpoint. So we then had a frantic few days to come up with the correction of the trajectory. That was done, and lo and behold, we ended up with perfect tracking. It's a big success item. Okay, the next slide, Delamere 2, shows the observations that we took from minus 60 hours to plus 15 hours from closest approach. And you notice that we are taking a pair of images every other orbit, and then lots of images in the right-hand slide. You'll see lots of images we were taking at the 3 close approach orbits. In the next slide, you see all 54 of our observations that we took with our red filter. Our blue filter, we have not yet finished processing the data for it, and and we're hoping to get a lot more information when we successfully get that done. So this is a falsy calori image, so it is purely and simply showing you a lot of the detail of what's happening in the coma. And the coma is really, really important for a number of reasons. One is we need to know what the outflow is from the comet and how that the direction of it, so we can then correlate that information with, for instance, all the ions that MAVEN has been describing. So there's lots to be done with these images in the future. So let's look now at the next view graph, the peak brightness as the comet passed Mars. And here you'll see that obviously it's varying significantly, and there must be some reason for the variation. And the answer is the comet is rotating, and the rotation period is about 8 hours. We have a lot of interesting information in this, and it'll be very interesting to see what we speculate in the long run of the exact mechanism of the rotation. With normal old comets, we get active regions that put out a jet, and as the comet rotates, that jet gives you that rotational information. What we're seeing with Siding Springs is somewhat different from normal comets. We don't have a number of strong jets, so we may have the comet behaving, since it's a new one, quite different from our previous expectations. So all of this is going to involve a lot of intense debate in the months to come as we untangle the details. But basically, we have an 8-hour rotation period. This rotation period is really important for us to know, because when we're at closest approach, two things are happening to us. One, the comet's rotating, and the other is our viewing direction is changing significantly during the observations. So now, to get a feel for all our observations in movie form, in Delamere 5, you can click on the movie and watch observations taking place in time. The observations, since they are taking place at irregular intervals, make it rather difficult to be able to fit everything mentally together. It's a little mental confusion that we have to untangle for ourselves. That one picture that flashed up high was a saturated image that will give us some more details on the coma when it's in the close thing. So moving on to the next slide, you'll see our 5 closest images during that orbit. And none of those are saturated. They're showing the actual pixels. Each of those pixels varies from around 140 meters for the first top left down to 177 meters. And there's about 50 pixels by 50 based on the comet. So what are we looking at? I mean, we're seeing pixels, but what do they mean? Is it the nucleus or is it the coma? And the answer is it's both nucleus and coma. How do we separate the two? Well, that's our challenge that we've got ahead, trying to work out which of the signal is coming from what. Now, I mentioned Comet Halley earlier. Comet Halley, we got some pretty interesting picture, but it had exactly the same solar phase angle as Siding Springs, which means the sunlight is coming from the side and slightly behind the comet. So one end of the nucleus will be illuminated, and most of it is going to be in shadow. Now, with Halley, we were able to see the outline of the nucleus against the coma. So as we're looking towards the comet, we see a very definite boundary. Now, we were hoping to see the same thing here, and so far we haven't been able to detect it. And that's now part of our ongoing research to try and work these images very carefully to separate coma and nucleus and see if we can come up with a much more definitive size. Right now, the size of this, if you look at those pixels, you could imagine just a few hundred meters of illuminated area on the comet. So the size of the comet could be even as large as 2 kilometers, or it could be as small as, a few hundred meters. So we have exciting times ahead in order to untangle that. Okay, moving on to the next one. It's an animation of the overall encounter. So for this, we've got the MRO spacecraft flying by Mars, and that spacecraft, of course, its primary goal is looking at the surface of Mars. So in order to look away from Mars, the logistics of moving the solar arrays and getting everything set up and aligned is a very complex operation. So the spacecraft team did a magnificent job at pointing HiRISE right at our comet. And there you see it in glorious black and white now instead of false color. The quick summary over that. Okay, now I'm just looking for, the next slide, Delamere 7, is data that's been obtained with CRISM. During the planning session, we arranged observations between HiRISE and CRISM to optimize both instruments' performance. And this slide is showing the results, the early results from the analysis of the CRISM data. The spectrum on the right is showing a flattish spectrum, which is suggestive of just reflective light from the dust. There's no emission lines or anything that's detecting any significant minerals in that process. But that's very much what we expect. The surprise that we have is the image on the left. Now this was taken a few minutes before closest approach, and the scale in this one is 4 kilometers per pixel. So you see that's radically different from HiRISE. And we need to fit the HiRISE and CRISM images together to try and understand this in more detail. But you see that it's slightly blue on one side and slightly red on the other, which means that we've probably got significant particle size differences on one side of the comet to the other. And translating that is going to take our team quite a bit of effort. With that, that finishes my presentation and pass it back to Jim Green.
Thank you very much, Alan. Well, comets really have been seeding the planets in the inner solar system for billions of years, and doing processes like this and spraying material that we pass through, and of course, even impacting the planets over time. We've been really extremely privileged to be able to observe what happens in this type of event. And as you can tell, we have a lot to learn. This has really been a tremendous event that was planned well in advance. And I want to thank all our science colleagues who participated in the Planetary Science Division, also in astrophysics, heliophysics scientists, and of course an enormous amateur community participated in. And their images that are being posted as taken from the Earth have been just stunning. Comet sighting spring has one thing in common with most of our other comets, and that is it surprised us. For instance, we had modeled the comet dust environment extensively, and we didn't believe that it would cause any problems with the operation of our Mars spacecraft. But now, after observing the effects of Mars on how the comet dust slammed into the upper atmosphere, makes me very happy that we decided to put our spacecraft on the other side of Mars at the peak of the dust tail passage and out of harm's way. And I really believe that hiding them like that really saved them. and it gave us a fabulous opportunity to make these observations. And with that, let me turn it back over to Dwayne.
Thank you, Jim. Thank you to the science team. Congratulations. So, operator, let's go ahead and transition into the Q&A, and I will toss it to you.
Thank you. As a reminder, if you would like to ask a question, please press star followed by 1 on your touch-tone phone. You will be prompted to record your name. To withdraw your question, you may press star 2. The first question today is from Seth Bornstein with the Associated Press.
Yes, thank you. I have one question and then a follow-up. For Jim, these are all orbiter data and images that we have, and you do have some resources on the Martian surface. I guess to me, as a person who lives on the surface, the fascinating thing is what it would look like from the surface. Do you have any image there, or could you tell us, given maybe you or some of the other scientists, tell us, given what we know about with the magnesium and the iron and the changes in the ionosphere, what it should have looked like from the surface looking up? If you were a Martian, and why don't we have anything like that from all those little lovely rovers you got?
Okay, great question. Of course, both Opportunity and Curiosity put in place to take a look up and see what was going to happen. Opportunity did have a chance to see it. Some of those early observations were posted right away. They're still looking in the Curiosity data, and what we're finding out is Mars's atmosphere had a fair amount of dust in the mid-region of the atmosphere, and that caused probably much more of a scattering of the light rather than, if it was very clear, it might have been really quite obvious from a comet perspective. Now, relative to the meteor storms, there probably was so many that there was just a general brightening going on. Plus, Curiosity and Opportunity don't really take movies. They don't really capture things very quickly. And so it's not quite like having a human standing there really in awe. They just weren't designed to be able to do that. But indeed, we're continuing to do data analysis in those areas, and those scientists will continue to work on those and continue to publish the results.
And just to follow up, in terms of what this tells us, in terms of the metal deposit into the atmosphere, is there anything that this could tell us about early either life or early Earth, in terms of as an analog, what may have happened to either seed Earth or with anything? I mean, what could this tell us about Earth? Looking at that, what you're seeing on Mars.
So what we do know is we believe that comets were formed very early, and much more earlier than the Earth was, and so they're really those very primitive bodies that tell us, give us a hint as to what was in the contents of our collapsing cloud that formed our planets and the solar system of inner planets. The comets, we believe, the Orcyle comets were formed early, but also through gravitational interactions were thrown out. And so that puts them in at the far reaches of the sun's gravity. Little tugs and pulls eventually bring them in. And it's through that process that we're able to see now that indeed all these heavy elements must have been either generated or came close to the comets were generated close to the sun and then thrown out much further. The whole dynamics of the solar system has to really be considered to be able to place these observations in their context.
Thank you.
Thank you. The next question is from Irene Klotz with Reuters.
Hi, thanks very much. I have, I think, two questions. I guess the first one, just following on what you just said, Jim, about the metals in the comets. I was wondering if, and maybe, I don't know who would be the best to ask this, but do you see any, and I know this is early, but do you see anything in this kind of trove of data that shows a difference between such a pristine comet as Siding Spring and some of the other comets that have been studied so far? That's one question. And then the other one, Jim, can you just be a little more specific of the damage that could have happened to the orbiters if they had not been behind the planet during the peak? Are we talking like, destruction from dust? Are we talking electrical interference or what? Thanks.
Okay, so let me take the last one first, and that is with the amount of dust that came in, it's very possible that these are not just micron size, but they can be quite large, perhaps up to a centimeter size. And anything that is of any size could easily destroy a spacecraft given its high velocity and hitting it in the right location. So we're speculating that the spacecraft would survive, but I think it's pretty obvious they wouldn't have, based on the tremendous response of Mars's atmosphere to the comet tail. Now, relative to how this comet compares to others, because this is an Oort-Cloud comet, and as Alan discussed this, and he really should probably comment on this too, we may be looking at a pretty fresh surface. In other words, it probably never has been into the inner part of the solar system before. And in our short period comets that we see all the time, they're just coated with dust. So as the outer layers sublimate away, some of the dust leaves, but a lot of dust stays on the surface and coats it, becomes a hard coating. And therefore, they're more prone to jets, where material is lofted through very localized regions on a comet. Rather, this comet might be very different, in a pristine form with no hard dust coating on it. We really, as Alan mentioned, might just be observing, based on a shape, that rotation, that light curve is not just about jets, it's about the rotation of the whole object.
And Alan, this is Dwayne. If you would like to add, and any other scientists that are on would like to add to any of the questions so far. Alan?
Well, you're touching on a pretty delicate topic here, because the Comet modelers, I spent quite a bit of time with them when we were going through this some time ago, and big particles, in order for them to reach Mars, had to have left the comet somewhere like 4 or 5 AU away. So you end up with two types of particles in the. Can you imagine a tube around the comet of dust and particles, and Mars went through that tube at a fairly significant distance away. So you'd see two types of particles. One, the very fine dust that comes off the surface continuously, and then you could have some old particles that have been drifted away from Mars a long time ago, and they could be fairly big chunks for all we know. But since we're seeing comets basically ice and CO2 and CO, all that stuff evaporates fairly quickly when you get into the inner solar system. So the idea of things clumping together into big chunks to make things exciting as meteors is probably pretty slim. It's probably very much the fine dust is what we were seeing in these meteor showers, as opposed to large, bright things like meteors we see here on Earth.
This is Nick Schneider. If I could offer another perspective. And I'd like to point out that not only is this a free sample of an Oort-Cloud pile of dust added to the Mars atmosphere, but it's so it's different being an Oort-Cloud versus a Kuiper Belt comet. But getting the sample in the atmosphere really gives us a chance to learn about Mars as well. We already have some signs that the chemistry of Mars and how it reacts to comet dust is different. And what makes me optimistic about being able to learn about both of these phenomena is that we have a treasure trove of data from all these different instruments on all these different spacecraft that are looking at the events, and I think we're going to be able to put together a coherent picture. And it's especially valuable that we have these observations of the metals in the atmosphere from MAVEN and the observations of the ionosphere that they created in addition. And I think putting all this together is going to help us solve two problems.
Could I just follow up real quick, Dwayne?
Sorry.
Thanks. I'm sorry to add, I just needed a clarification of something. I was a little confused by something Alan just said. Were the metals in the Martian atmosphere and then ionized by the comet dust, or did the metals come from the vaporization of the comet dust? Thanks.
I'll answer that. It's definitely the latter, right, Nick?
That's right. The comet dust contains metal, and I should say that it also contains a lot of other ingredients from rock, but those elements are hidden underneath the signals of other atmospheric gases. So it's most certainly the metals which are common in comet dust, which were freed from the particles and the minerals that they were in through the tremendous heat as they entered the atmosphere.
Thank you. The next question is from Bill Harwood with CBS News.
Yeah, hi. Really, two questions. The first one's really for anybody. I'm trying to get a sense of, we keep talking about a meteor shower, meteor storm, or whatever. I know the rovers couldn't quite see this. What would I see if I was standing on the surface of Mars looking up when this happened? I mean, is there any way to get some sense of what that would have looked like? And I have a follow-up.
So I can take that one, Jim, unless you want to.
And who's talking? Thank you.
Nick Schneider.
Yeah, please do, Nick.
So I'll start out. Ours is the instrument that was able to measure the amount of glow from magnesium in the atmosphere, and it's actually about 10% by mass of comet dust, and that allowed us to figure out the total amount of mass, which is probably thousands of kilograms. And this is the estimate which has allowed us to say, what do you get if you break it up into particles the size of a grain of sand and have a meteor shower that lasts really just an hour or so. And that calculation says that there probably were thousands of shooting stars per hour. And I don't think anybody on the phone has ever seen that. It's extremely rare in human history, and it would have been truly stunning to the human eye. Now, we've got all these high-tech robots around, but I have to say that it might be the most sensitive scientific instrument of all to have a human lying outside with dark adapted vision looking up at that sky and to see many shooting stars happening at once. I think it would have been really mind-blowing.
Thanks. And a second question for Alan Delamere. I just wanted to clarify what the thinking is on the range of sizes we're talking about of some of the particles. In other words, do you think spacecraft would have been are we thinking like really tiny dust particles is what the most of this was, or could there have been some bigger stuff that could have taken out a spacecraft? I realize there's no real answer to that, but I'm just trying to get a sense of the range of sizes. Thanks.
Okay, you've answered your own question there, because we're talking about micron-sized particles in the dust, and when you start dealing with any dust collection, the distribution of particle size falls off. So you go from 1 micron to 100 microns, and then eventually you may end up with a centimeter, but that's probably as far as it's likely to go. This is a new comet, and that's why I'm sort of being somewhat negative about the 1 centimeter size and above.
Okay, thanks.
Thank you. As a reminder, to ask a question, you may press star 1 on your touch-tone phone. The next question is from Kella Cofield with Space.com.
Hi, this has been sort of discussed in the last few questions, but I'm just curious. So you said, Jim, that it was sort of a surprise. You really didn't expect just how hard the dust was going to hit the ionosphere. So to clarify, what was the surprise factor? What didn't you anticipate, or maybe what have you seen, that was just unexpected here?
Yeah, indeed, we did a fair amount of modeling. This is Jim Green. A fair amount of modeling. Had actually 3 of the expert teams taking observations that were done by our telescopes, both in space but also ground-based telescopes, and then modeling the dust environment, and then looking at trajectory analysis. And the analysis seemed to indicate that Mars would miss the dust tail in a significant way. In other words, if we were, as the comet flies by and the dust tail actually is following the trajectory, and we move close to that trajectory, as the dust tail fans out, it still would not have reached Mars in any significant amount. The surprise is that indeed the dust tail seemed to be larger. The other surprise, perhaps, and we haven't completely done this analysis, is the comet wasn't quite in the same position as we thought it was. As Alan mentioned, this was an important set of observations MRO did very early on from a Mars perspective that got the actual trajectory right, and therefore it had the advantage of really allowing us to get great observations from MRO of the comet itself. So that all has to be factored in. And so indeed the surprise was we ended up with a lot more dust than we ever anticipated.
Thank you.
Thank you. Our final question today is from Seth Borenstein with the Associated Press.
Yes, thank you. This is to follow up on what Nick Schneider was telling Bill Harwood. I could have sworn you said, looking at the dust, you measured that you assumed that now that there were thousands of kilograms of dust. I want to make sure I heard that right. Any guesstimate on how many thousands of kilograms of dust? I mean, that's an awful lot of dust.
It is a lot of, Nick Schneider answering, it is a lot of dust, and I have to be clear that this is a very preliminary estimate. It requires a lot of calibration and verification, which is why we really can't give any more than a round number. I think there are two perspectives. One is that, a few thousand kilograms, you can't quite take it away in a pickup truck, but it's pretty small. But if you do break it down into dust, you can make quite a meteor shower. But we're not prepared to give you a more precise number right now, but our team is working hard on it.
And in terms of the other part of it is magnesium, I mean, forgive my poor chemistry, but I seem to recall that magnesium gives off in general here on Earth, a different type of glow. Was there any color that, to build on Bill's question, if you were standing on Mars, it would have been just bright white, or what? Is there any color you would have seen? I mean, if you could just help us paint a picture, since we don't have one from the rovers.
Nick Schneider answering. Yes, I do this kind of visualization in my mind's eye a lot. I think it's some of the real return of science. We've talked a lot about the ultraviolet glow because that's why our instrument is tuned. But all of these metals have emission lines, or we would say scattering lines, throughout the spectrum. One of the most prominent things that an astronaut on Mars, what he or she might have seen, would be a yellow glow from the sky. And that's because sodium is also a common element in rocky material, and it's everybody actually knows this color because a lot of parking lots, a lot of city lighting is low-pressure sodium. And it's very likely that the meteor shower would have left a layer of sodium atoms high in the Mars atmosphere, similar to a sodium atom layer in Earth's atmosphere, but I suspect far brighter. And so I think this yellow afterglow, visible especially in twilight, would have been a very pronounced phenomenon.
Okay. Thank you.
Thank you. And I'd now like to turn the call back over to Dwayne Brown for closing comments.
Thank you, operator. I want to thank folks for joining us this afternoon. A reminder that you can hear this telecon in its entirety with a replay all the way up to November 14th. That replay number is 800-947-6766. That's 800-947-6766. And, of course, additional information, updates, images all on the web at mars.nasa.gov/comets/sighting spring, all one word, mars.nasa.gov/comets/sighting spring. My congratulations to the team, and I'm sure that more details and analysis and other information will be coming out, and we'll be sharing that with you as soon as possible. Thanks for joining us, and over to you, operator.
Thank you. This does conclude today's conference. Thank you all for joining. You may disconnect at this time. Speakers, one moment for